So the question is, when we're thinking about collections, we want to understand what the requirements are for collections. And there are different kinds of requirements. So for example, you want to be able to test whether a given item is in a collection. There's a kind of element of or membership predicate that is important. In general, it seems a reasonable request that that collections are monadic, in the sense that you can take a thing of type A and put it into, if C is your collection, then you can put an A into a C C of A kind of collection. So that's a unit. And then you also want to be able to roll up collections. So if I have a collection of collections, and I have to be able to form those, since if I can put anything, something of type A, and I don't know what A is, into a collection CA, then I could take something of type collection CA and put it in a collection, giving me a collection C of A, right? So since I know I can form those, I need to be able to roll those up. So as an example, if I have a set of sets, I can, in a canonical way, union all the sets, all the lower level sets together and get one big flat set. So that flattening or rolling up operation is at a minimum the kind of thing that we want of collections. But it turns out that that the power gadget, so the set of all sets, as an example, the graph of all subgraphs of a given graph, as another example, that is also an important requirement for this kind of setting. And what we're interested in is how to use the guidance of the power set to smoothly extend that to the linear setting. And it's clear that, it's a little bit more complicated than the set of all sets, because, for example, you don't have straight up intersection and union kinds of operations. So you have a tensor product, some kind of tensor operation, and you have which is multiplicative in the sense that it doesn't respect the most basic thing of so like intersection of a set with itself is just the set, right? But the tensor, if I have some proposition A and I have another version or copy of that proposition A, when I tensor them together, that's not the same as A. So if you want to think about it in terms of resources, this makes a lot of sense. If I have $1 that I got from one transaction, and I have another $1 that I got from a different transaction, and when I put those two together, I have $2, not $1. So it's a very different kind of setup, the linear setup, and we want to be able to see how the power set construction, that the monad that is associated with that power set can be smoothly extended. Oh, it turns out that there is such a construction in this paper that I have on the screen. provides that construction, provides actually a whole recipe for a wide range of situations that all follow this basic pattern. And this is going to fit into the construction that we that Christian has been exploring, where you take Yoneda as the first step. So you go from the theory to Yoneda. So so you're looking at representables, and so essentially it's a pre-sheaf construction. So this is going to extend that construction. So instead of sort of the Yoneda category, we get a V Yoneda in category or V enriched Yoneda category. And the trick turns out to be quite simple. Let's see if I can find the basic. I mean, I can write it down. I just wanted to see if I can remember where it is here. Yeah, their language is going to be a little bit tough for this crowd. So here's the. Let me bring up a. Okay, so the basic idea is. Let me get. All right, I'll just use this one. Suppose I have X cross Y, and I send it to the set 2. I should be able to. Can everyone see that?
Yes.
Okay, cool. So I can, whereby 2, it's just the 2 element set. I can interpret this as a relation between X and Y if whenever some pair, little x, little y, is mapped to 1, then I say that they're related. And if little x, little y is mapped to 0, then they're not related. So this particular way of carving up or describing relations gives us a smooth transition between the power set monad and the category of relations, sets and relations. So the category of sets and relations is going to have, sets as the objects and relations as the morphisms. And then relational composition is the composition, the identity relation is the identity, and clearly composition is associative. So that's clearly a category. And this little device here that's on the screen, essentially what it does is it makes that the Kleisli category of the power set monad. So the power set monad, given a set, it takes that set to the set of all subsets. So the Kleisli category of that monad is going to be, the objects are still sets, and the morphisms are going to be, normal morphisms, but in the underlying category, but from X to power set of Y. So rather than X to Y. And then when you do composition, you have to whack it with the mult, the flattening operation on the other end to drop it down, right? So you hit everything with the unit. So you have x to monad of y, and then you want to compose it with another, y to monad of z. So you whack that one with the unit, so you now get monad of y to monad of z, right? So now you can compose the two, but you have monad of z, and so what you have to do is flatten that thing. So you hit it with the mult on the end, and that's how you do composition in the Kleisli category. Does that all make sense?
Yes.
Okay. Yes. All right. So, so then it turns out that the category of relations, well, the dual of it, is Kleisli to the power set monad. So we can use this idea to generalize the whole construction. So in particular, 2 is also what's known as a quantale. So a quantale is a soup lattice. So you have all joins, and you, but it is also equipped with a binary tensor operation. So if you think about joins as like union, you've got some underlying set, and you've got some set of subsets, and whenever you have two subsets in the thing, then the union of those two subsets is also in your thing, whatever your thing is. So here our thing is a quantale. But we also have some binary multiplication-like operations. So we want to be able to multiply subsets of a given set. So the way that's done freely, if you wanted to generate the free quantale, you start with some set A, you consider all finite sequences of elements of A, and then you consider all the subsets of all the finite sequences. And now you have a multiplication operation. So if I have, obviously I can multiply two sequences by concatenating them. If I have two sets of sequences, then I can consider all concatenations, and that gives me the multiplication. So that you can keep that image in the back of your mind when you're thinking about, well, what is a quantale? So 2 is a very, very simple quantale. You've either got the empty set, or you've got something which represents, everything. It's the truth value. So it's all gadgets. And so, all the sequences. So then clearly you can, the meet and the multiplication collapse. So you don't have a distinction between, the meet is dual to the join, and the meet collapses with the multiplication, and you're back at ordinary power set. But if you have some arbitrary quantale, Q, then you can think about something like this. So if I have little x comma y, and I've got, we'll say that they're related by R. if it goes to some element Q living inside Q, and now Q is giving you the quality of the relation. So if you're down at the bottom of Q, then they're unrelated. But as you climb through the different levels of Q, then that result tells you sort of how or with what quality X and Y are related. So if you had, for example, the 4-element quantale, so you have top and bottom, and then you have 0 and 1, so it forms a little diamond, right? Top is at the top, bottom is at the bottom, and 0 and 1 are not comparable with respect to the join ordering. Then you get then you can see that you get a slightly different notion of how X and Y might be related. And I think that's the next smallest quantale, is that quantale. Now, it turns out Abramsky and Vickers showed a very long time ago, some 30 plus years ago, that you can use quantales to investigate the semantics of processes. So you can get all the way up through 2/3 by simulation, or sometimes called ready simulation, using modules over quantales. So one way you might think about this is you look at the traces of processes, right? So you're looking at if say X and Y interact with each other, sorry, if P and Q interact with each other, then at X, then you, or whatever your label is, you might have a different labeling system. So the traces are generated by the labels associated with the COM events. So if you have some tree of COM events that's possible from a process, then the COM events, whatever labeling you give to those COM events, the walking from the initial process out to some leaf, assuming that there are leaves, walking that tree will produce a trace. So you can think of the trace like this, like the sequences in our free monoid example, and you can think of sets of traces as generating different pathways that would be associated with the tree of COM events. Does that make sense?
Yeah.
So go ahead.
May I ask, is there a relation between, you said quantale is also sublattice. So I'm trying to understand that. And are you saying that, and also you're saying Q can be a trace. And is this means that
Q is going to be some set of traces, right? So if big,
okay.
Yeah, it's not a single trace.
Okay. Is this means that there is some kind of ordering in the quantale?
Yes, that's right. That's right. Since it's a lattice, there's an ordering. Yeah, it's a poset.
Okay. So lattice means some kind of ordering.
Yeah, some poset. Yeah.
And in the power set where you have all subsets, so this is also implies some kind of ordering.
Yes, clearly.
We know.
Yeah, the power set is a poset.
Okay, and when we have all of these subsets, we can combine them. And what if we have the same elements?
Then I mean, in the ordinary power set construction, that's what gives rise to Boolean algebra, right? Boolean logic, right? A and A is intersecting A with A, which is the same as A. A or A, which is unioning A with A, is just A.
Oh, I see. I see. We want that. Okay, in the Boolean logic. Okay. Oh, yeah, yeah. This makes sense.
Right.
But
But now
you,
if there's sets of sequences, so those properties will still hold for intersection and union. But if I do multiplication of two sets, that multiplication will not give you right. It won't give you the set you started with. So
I
A
see.
times A will be very different than A.
So this means a different kind of logic, right?
That's correct. That, and in fact, every model, so every quantale is going to be a version of, well, every finitely presentable quantale is going to be a version of the free quantale with some extra relations.
Okay.
All right. But now here's the trick. The trick is that in the same way that power set is Kleisli to rel, then this other kind of power set, the power set, so the Q power set, is going to be Kleisli to Q relations. That's the name. That's how we're doing this. So we generalize from 2 to an arbitrary quantale, and then we get this. Then we get Q relations, which are Q, are going to be Kleisli to the Q power set construction. So now we get all kinds of different structures, right? They're all essentially linear logic-like structures, but they're all coming smoothly from that template that we got from the power set relation correspondence. Does that make sense?
Yes.
So in the same way that we're going to have a power set that's associated with 2, we're going to have a power set that's associated with every Q.
This makes sense.
All
this
right?
means we can have like arbitrary programs, right?
It means we're going to have a wide range of logics. 2 gives you Boolean logic. Q gives you some flavor of linear logic. That's the idea.
Okay.
So what you put over here is what's giving you the flavor of logic on the collection side. So remember, what we're trying to do is we're trying to look at Christian's construction and see if we can decompose it into a contribution that comes from the syntax of the programming language and a contribution that comes from the notion of collection. And so Christian goes from the theory via Yoneda, right? So he's looking at maps from sorts. He's looking at the representables, okay? And then but what we want is not set-based representables. We want a notion of representable that gives rise to an arbitrary collection semantics, or at least as arbitrary as logical consistency will allow. And that's where this construction comes in. This is at the essence of, at the heart of the Yoneda construction. And now we're generalizing Yoneda using this bit. That's what's going on. And so now we can move from Yoneda, from Christian's construction, which is basically from the theory via Yoneda to sub to Grothendieck. That's the sequence. So here we're going to go theory to Q Yoneda to sub to Grothendieck. And before, I was looking past the Yoneda bit as the place where the contribution for the logic was the collection part of the contribution was happening. But it turns out that if you look closely at where the collection operations are being interpreted, they're being interpreted in the first step. It's in the pre-sheaf construction. So we need a Q pre-sheaf, and that's what this is doing for us. You know, I mean, we have a lot of calculations, but the main trick now is to see what it means to have this, because that's going to force a requirement of an enrichment sort of Q enrichment on the theory. And so to make sense of that, we have to, well, the approach that I'm investigating with Mike right now comes from here. And this is where the lax extensions are important. So let me see if I can find it. It's right here. So it turns out that if you have a Q, but they're calling Q V. Okay, so sorry for the notational clash here. So wherever you see V, think what we were doing with Q for quantale. So suppose you already have this VREL situation, which we were just looking at. If you have a monad that has a couple of additional pieces, if you consider the opposite, I believe that O is opposite. Let me just double check that. Pretty sure O is opposite. By the way, here's the equations for the V power set, right? Which we were calling the Q power set. So this is the set of equations which give you the monad from the relational definition. Let me just yeah, it's opposite. Yeah, it is opposite. And that has to do with the duals. Okay, so notice that something interesting is happening here. So if you look at the opposite of mult, so it flips it around. Instead of going from t squared to t, it goes from t to t squared. And we have the opposite of unit, right? Instead of going from I'm sorry, we have the opposite of the evaluation function, right?
Is this the same as comonad, or?
It's not the same as the comonad, but it's got a comonad flavor to it, right?
Okay.
That's what's interesting, right? Because power set also has a comonad flavor to it, right? It's sort of, right? You're going from set to set of sets, right? So set to set of sets, right?
Yeah.
So that's quite interesting, right? It's certainly intriguing. And then you have to have some coherence in terms of how T, our monad, relates to the relations. So here are a bunch of coherence equations. I'm not going to go through them here, but you can look at the paper yourself. In other words, the monad has to play nicely with the relations. And so this is how I think well, it's one path to explore in terms of getting the monad to work nicely with the relation. What they're calling V relations are what we were calling Q relations. So in particular, think of this monad as the syntax for your calculus, whatever your notion of computational machinery is. So this is that monad. So like this would be the syntax for the row calculus or lambda or whatever it is, right? And now what we want is V to relate or play nicely with that monad. So one of the most natural things to look at, of course, is either traces or synchronization trees, right? Because those will generate, traces will certainly generate a quantale, right? And that quantile will be related in a nice way to the, so for example, something like this kind of relation. This is essentially saying, this is essentially preserving simulation, right? So if I've got some set of traces that's included in this set of traces, then if I put the thing that's generating those traces into the same syntactic context, then basically this is saying that bisimulation is a congruence, or simulation is a congruence, right? That's what this equation is guaranteeing for you. So this is the kind of thing that I think that we're exploring now in terms of all of our calculations. But it's a lot of stuff that we have to check. But the nice thing is that it's actually stuff that we have to check, as opposed to having to, work out the conceptual arrangement, right? So this basic pattern here, moving from 2 to Q, is the template, and it gives rise to a very natural set of things that we have to check. So assuming that we've got this, we've got the patterns lined up correctly, then these equations will either verify or not, and we'll learn quite a bit with however the calculations go. But this is the where we are right now. Does this make sense? Do you understand what we're driving at?
I think so.
Yeah. So again, what we're trying to do is to move from Boolean or intuitionistic logic to more general logics, and we're asking where the container part, where the container contribution is. The argument is that the container contribution happens in the Yoneda step. So we're looking at this Q extension or V extension of Yoneda, and then we're looking at how that has to interact with the syntax. And so the syntax and the operational semantics together give you a notion of a quantale that is a natural V, nay Q, to consider for checking the kinds of equations, and then that will give us the Kleisli power gadget situation that we were looking for. Hopefully, if we've got everything worked out correctly, and that would then give us a much more general template. So essentially, what it does is it says the distributive law runs into problems with negation. The Yoneda embedding overcomes some of the problems with negation, and this gives us the generalization of Yoneda so that we can have more logics than just Boolean or intuitionistic logic. That's the summary.
Can you a little clarify Yoneda and what is representable?
Sure. Absolutely. I do want to have a little bit of time before stand up. How about this? Okay. I will make sure next Casper to talk in detail about Yoneda. And yeah, because the Yoneda lemma is kind of the heart of category theory, in the same way that, there's a fundamental theorem of calculus, right? That you learn. I mean, like if you understand the fundamental theorem of calculus, you've really kind of understood what Newton's calculus is about, right? Or if you understand bisimulation and the notion of congruence with respect to bisimulation, you're beginning to understand like the essence of that notion of, the process-based notion of computation. Likewise, Yoneda is really at the heart of category theory. If you understand Yoneda, then you've really understood something essential about category theory. So it's worthwhile going into some detail about it.
Great, thanks.
Sure.
I was learning about Yoneda, and I was watching some lectures, but I didn't grasp the essence, and so I'm still struggling to completely understand.
Yeah, I mean I guess it's one of those. It's funny. It's one of those things that I always have to look up. But it's essentially for categories where the Hom gadget is a set. Remember, Hom gadgets can be lots of different things. They don't necessarily have to be sets, but for categories that are where the Hom gadget is a set, right? Then you have this way of thinking about a map from categories to the category of set, right? And so given any category that's sort of within certain boundaries, right? Then you can go from that category to the category of sets, and because of that, you have to you can build a model. You see what I'm saying?
Mm-hmm.
Coolio. All right.
Okay.
I'll see folks in the dev stand up in a few minutes. Thanks for your time and attention.
Okay. Thanks. Bye-bye.